Good morning. Today we are going to simulate a buck converter using MATLAB software. For that we have to do a certain procedure. We will follow the procedure. Let's see how we are simulating the buck converter. First we have to click on new file and you have to select the Simulink model. You will have an untitled page. In that untitled page you have to go to the library browser. In that you have to search DC voltage source. The DC voltage source is available. You drag it to the untitled page, place it here. Next we need a MOSFET. Let's take the MOSFET from the library, drag it to the untitled page and place it in the untitled page. Next we need diode. Let us take the diode from this page and place it here. Next we need current measurement block. Let's move the block into the page and place it here. Next we need voltage measurement for measuring the output voltage. So let's take the voltage measurement block and place it in our untitled page. Next we need series RLC branch. So we have to take series RLC branch and place, and we need 3 copies of series RLC branch, one for inductance and another for capacitance and another for resistive load. Now we are going to connect all these things together. Let me align each and everything properly so that it will be easy to connect. Just drag and connect to that particular point. I am adjusting in order to make an alignment. Next I am going to connect my current measurement. Before that I will rotate the MOSFET so that it will be easy to connect each and every block to it. Next I am connecting the MOSFET to the current measurement block. Next I have to rotate the diode. The diode is connected to the MOSFET. Next I have to connect the DC voltage source to the other part of the diode, that means anode part of the diode. I am just elongating it so that other components can be connected easily. Let us take the series RLC branch. You have to double click on it, left click on it, so that properties will appear. Just branch type, change it to L so that it will be an inductance. Keep the value as 10 millihenry. You can put 1 millihenry also, no problem. You can put 10 millihenry here. Just connect it to the main circuit. Next another series RLC branch should be turned into capacitance. So I am selecting capacitance. The value is 100 microfarad. So I have to type it. Just click apply and OK. Rotate the capacitance. Just connect the inductance and capacitance. Now this capacitance should be connected to the diode's anode. Next we have to use current measurement, so that I make a copy of current measurement. I am placing it in the right place. I am going to connect the current measurement to the inductive capacitive circuit. I am just making an alignment. Next part is to connect the R load in my circuit. I want to change this series RLC branch into R load. I am just making the changes, and I am putting the value as 10 ohms. So I want to rotate the resistance now. It will be considered as R load. It should be connected to the current measurement block. Next, it should be connected to the capacitance anode combinations. Yeah, it's connected. Next, we are going to connect the voltage measurement block across the load. This is how we are connecting the voltage measurement block. You can make changes, alteration by adjusting, by moving the voltage measurement block. Next, we need a scope for seeing the output. So I am just taking the scope from the library and placing it. I'm just magnifying the scope. I will change the scope name as power circuit. Since we are simulating the power circuit now, I am renaming it as power circuit in the place of scope. Now it is having only single axis. I want to change the number of axis. I need 5 axis or 4 axis. Now I am going to put 4 axis in my scope. Next, I need go to block, right, but go to is not available. I hope so. I want to type it properly. Again, there is a mistake, right? I'm searching for go to tag, so I need to minimize the space. Now I'm putting tag to showing go to tag visibility, but now I'm removing the space. Now it is go to tag visibility, right? There is a go to tag. Now I want to take that go to tag. Instead of joining each and every line to the block, I can use go to tag such that lines will be reduced. Then I need a from block, from where I'm going to get the output, from where it should be going, right? For that, go to is needed. So normally we need go to block in current measurement. From the current measurement, it should be sent to the scope, right? So we need go to block. I'm putting IS in the current measurement since it is a source current. Next, I need another go to block. I'm going to connect it to the voltage measurement block. Yeah, it's connected now. I want to rename it. But later we will do that. Another thing is needed, that is display, right? So we have to take the display from the library, and I want to connect it to the next to the voltage measurement block. Now it's connected. I'm renaming the voltage go to tag as VL, that is nothing but load voltage. Another go to block is needed. It is for the current measurement. What is the current flowing through my load, that is needed. So I want to rename it again. It is represented as I L, that is nothing but load current. Just press apply and OK, that's all. So go to tag has been placed wherever needed. Now we need from block because we have to provide the gating pulse for the MOSFET. So I need one from block that is to be connected to the gate of the MOSFET. I will rename it as G since it is gate. Next, this from block has been copied and it is moved and connected to the scope directly. This shows gate, and another copy of from block is taken. Likewise, I will be taking number of copies from copies and making a light adjustment so that it will be looking proper. I will rename all the go to tags as well as from tag. Right now it is renamed as IS. That is nothing but it is going to display the source current. Instead of connecting each and everything to the scope by individual wires, we are using this thing. This from tag is another copy and it should be renamed. I will rename it as IL. Next thing, another from copy is there. I have to use it. I will be connecting it to the scope and I have given the name as VL. It is nothing but load voltage. Now each and every go to block has been connected to from, so that we may look over the output in the scope after running the results. Just alignment has been taken care of. I hope everything is now aligned in a straight line. Just we are seeing the amplitude is DC voltage is 100 volt. I am just renaming the series RLC branch as inductance L, and another load is typed as R load since we are using resistive load, and renaming the series RLC branch as capacitance C. So that's all about the power circuit. We have designed the power circuit needed for the buck converter. Now let us move on to the control circuit. For that we need repeating sequence. That is nothing but triangle wave generator. This repeating sequence has been taken. Why this repeating sequence means? This repeating sequence will be considered as a triangle wave. Next we need a relational operator. The relational operator is used for comparison between this triangle wave and constant wave. So we have to take a constant source. So this constant source has been taken and it has been placed in the untitled page. And then we need slider gain. Slider gain is needed in order to vary the duty cycle of our converter. I am just magnifying the relational operator so that it will be visible to connect each and every component. I am connecting the repeating sequence to the relational operator. I am just adjusting for the straight line formation. I am just connecting the constant to the slider gain and slider gain to the relational operator. Just magnifying, little bit alignment is going on. I hope now it is getting closer. Yeah. Now we have to set the values of repeating sequence. We have to set the time values. I am using the frequency of 100 kilohertz, so I am having the values of 0.00005, that is nothing but 1 by 100 kilohertz, and another one 0.00001 is nothing but the value which we are entering. And for output values, the origin point is 0.1 and the highest magnitude is 5, and again the lowest magnitude is 0.1. These are the values that I am entering into the repeating sequence. So the waveform is changed into a triangular wave. It is compared with the constant wave by means of relational operator. We have already used a slider gain. Now we need data type conversion block. This has to be connected to the relational operator. Through this means only it is going to provide the pulse to the gate in the power circuit. So we need another go to tag, because you have to send the pulse generated through this go to tag to the gate of the MOSFET, right? So we need that one too. Before that, we will be connecting the go to tag in various places. First go to tag is named as T1 in the control circuit. I'm just making another copy and I'm renaming it as before that it is not aligning properly, so I will make an alignment first, make a connection. Yeah, it is connected now. Now I will rename it as T2. Next, another copy of go to tag is needed. I'm just connecting it to the converter block. It should be renamed as gate G, since it is going to provide the gate pulse for the MOSFET. So I'm going to save it. Now we need another go to tag for connecting, that is nothing but it will be connected before the gate pulse. So it is represented as T3, so we will change the name as T3. Let's save the value. That's all about our control circuit. Next we have to take the scope, I hope so. Let's take the scope and place it in our untitled page. Magnifying the scope so that it will be very clear. Now we have to improve the axis, so I'm going to use 2 axes. So I'm making the changes. Next, I need a mux in order to connect multiple inputs, so I am using a mux. Now I am going to use number of inputs as 3, so the 3 mux will be connected, 3 inputs can be connected, and you will get one output, and it is connected to the scope. So the inputs are nothing but from tag will be used. So I am copying a from tag. I am just connecting this from tag to the mux. 3 from tags are used. The second from tag has been connected to the mux. Now I need a copy of it, so I am making it a third one. Again it is connected to the mux. So I want to rename each and everything. I have to put T1 in the first from tag. In the second from tag I have to put T2. And in the third one I have to put T3. And finally I have to connect a gate tag to the scope, right? Gate from tag to the scope. I'll make a copy of it. I'm connecting it to the scope. I hope all set. I am renaming the scope to control circuit, since it is a control circuit. Now let's go to the library and take a power guide block. Without this block you cannot simulate anything in your MATLAB. That is nothing but power graphical user interface. You have to change the continuous into discrete, and you have to change the sample time as 1 microsecond. Now you can have a test run, right? Test run, it is giving, we are having input voltage of 100 volt. Now it is providing an output voltage of 9.26, right? It's a test run. Let's check. First, before that, we have to save this MATLAB simulation. I am going to save it as test 2. It has been saved. Now let me try to run again the simulation. Now it's running. My output is 9.268. My input is 100. It has been stepped down. Now we need a more output, so I am going to vary the slider gain. My highest value is 5 and my lowest point is 4, or middle value is low. You can set like that. Lowest value is 0. Now you are going to run. Now you can see that the voltage has been stepped down to 69.27. You have given 100 volt as input. In output you have seen 69.27. It has been stepped down by this converter. Now let's see the scope of the power circuit. You have to press auto scale. So this is your output. You have to scale it, right? Now you are getting certain waveforms. Again it is not clear, so we have to scale it again. You are getting some waveforms. You can change the scales such that you can get the desired output waveform, right? Your scales will be readable. Now you are getting each and every waveform. You can see the output voltage 69.269. If you are dragging each and everything, then you will get a straight line, that is DC voltage of 69.269. that is your last scope result. You can rename it as you wish. I am just renaming the title of my scope load voltage. That's my last scope result, right? I am just renaming the axis. Now if you give auto scale, it will align. You can see it is 69.269 what we have seen in the display. It is shown in the scope graphically. Similarly, you can see all of the parameters and you can change. So you can rename as you wish. So I am renaming the next axis. There is nothing but it is load current. If you put auto scale, you will get something. Yeah, you are getting current value. You are getting load current, load voltage, each and everything. You are getting a waveform. Likewise, I am going to rename the next axis. It is gate pulse that we are providing to the gate. You can see the pulse. Renaming it as source current. Next axis is source current. I am just renaming it as source current. And the next axis is load current. I am renaming it. So now you can see the load current and load voltage. Gate, source current, load voltage. Right. I can provide auto scale. Getting the output. getting the values. As we are getting each and everything, load voltage, load current, everything is proper now. We are getting almost 6.9 load current, and then in the case of load voltage we are getting 69.269. Now we can save the result by means of using the paint, and just print screen and paste it in your paint. Now right click on your output and just select invert color. The colors will be changed. So white background, and then you will be getting blue color as your graphical result. You can crop if you need, right? If you need only results, then you can make a crop in your outputs. Otherwise you can save as it is. Save as JPEG image in your desired location, and that is the needed. You can save in your desktop or somewhere else, so it will be saved output. And just rename it as output in my desktop. This is the output of a power circuit, right? Similarly, now we can see the output scope of control circuit. Now I'm just pressed auto scale. Just I'm making a scale adjustment so it will be visible for you. You can see a triangular wave is compared with a constant wave, and you are getting a PWM pulse, right? A violet line constant, yellow line triangular wave, and a Turkish blue, it is your gate pulse. And the next axis, second axis, is your output gate pulse, that which you are going to feed it to the gate of the MOSFET. Just print screen and save similarly as you did earlier. If you need to change the color, then right click on the same thing and put invert color. Now you are going to save it in the desktop. So these are the results that we are obtained from the simulation. This is the entire circuit of buck converter. I hope it will be clear. Now to simulate, by means of adjusting the slider gain, you can get the desired output, right? Now you can see I have adjusted the output to 49.35 volt in the output, right? Likewise you can do anything else. Again 69.27. Likewise you can, by means of varying the duty cycle, you can get the desired output, right? Now I'm just varying the duty cycle again. Let's see what happens. I'm just changing the values of slider gain. Now you see you will get the output voltage around 9.26 volt. So by means of varying the duty cycle, you are varying the output voltage. That is the concept here. Thanks for listening to the session. Thank you.